Hello. Today what I want to do is solve a problem on electric fields, and I chose one system that was similar to the one we discussed the other day. It's three charges in an equilateral triangle configuration, and what I want to do is remove the charge at the apex, redraw my triangle like this. So I have a 2 microcoulomb charge here, 4 microcoulomb charge here, and at the apex this is a point in space. So let's pretend there's nothing there right now. And what I want to do is I want to determine the electric field at point P due to the other two charges. So first thing I want to do is draw the electric field vectors. We know that for a positive charge, the electric field is directed away from the positive charge and towards the point in question. And so the electric field is directed up towards P. I'll label it E1. The electric field due to the negative 4 microcoulomb charge is directed towards towards the charge because it's a negative charge, and away from P. So electric field is directed in that direction towards the charge. I will label this E2. And now what I'm going to do is break this up into each electric field vector. I'm going to break it up into X and Y components. Remember that this is an equilateral triangle, so all the angles are 60 degrees. So the X component of E1 looks like this. The Y component of E1 points upward. E1 sine of 60. And then for E2, I'll actually draw this component in red because we're running out of space here. The X component of E2 directed towards the right. So this is the magnitude of E2, cosine 60. And then the Y component of E2 is the magnitude of E2 times the sine of 60, but it points downwards, so I'm going to put a minus sign there. Now remember, the magnitude of the electric fields due to either one of those charges is written in the following manner. K times the absolute value of Q over R squared, where R is the distance from the charge to the point in question. In fact, it's the square of the magnitude of the vector that's directed from the charge to the point in question. Okay, so for E3, let's write E3. I'm sorry, not E3, E1. Give me K. And by the way, again, I apologize, I'm suppressing the units because I'm probably not going to have enough space here. And R is half a meter. And I just write it in unit vector notation, so a little bit easier. So I'll write it like this: cosine of 60 I hat plus sine of 60 j hat. And then E2 8.99 times 10 to the ninth. And the units, remember, are Newton per meter, Newton meter squared per Coulomb squared. This has units of coulombs. And notice I'm putting the magnitude of the charge here. And I divide by the distance squared. And again, here I'll put, this is essentially a unit vector, right? This is just a unit vector I'm putting here if I'm writing this in IJ notation. And so I will put here the x component is cosine of 60. Oops, I had. And the y component is minus. Let me make sure you can see these decimal points. All right, so E1, if you use your calculator, turns out to be and I'm not going to be careful here with sig figs, I apologize. So it's 36,000 at hat, and then the J component is 62,350 J hat. And E2 when you work this all out on a calculator ends up being 71,900 I hat minus 124,600 J hat. And both of these had units of newtons per coulomb. Now I'm going to add them. When I add them, I will get 107,900 I hat. And I'll get negative 62,250 J hat. And that's it. Now, if I take a charge that's 7 microcoulombs and I put it here, then the force is just Q times E. So if I want to find force on a charge that I place at this point, so place a 7 microcoulomb charge at point P, then the force on that charge is given by Q times E. So I take the Q, multiply by E. And guess what? We get the answer we got the other day. Which was, and I'll write it just in IJ notation. That is the value we got the other day. So there's another way if you want to calculate the force on the charge in some sort of configuration. You can calculate the field first and then multiply by the value of the charge. We would call it the test charge, and you get the force on it. If you're ever given a problem where it asks you, find the location where a charge is in equilibrium, you really don't have to solve for the force. You just have to find the location where the electric field is zero. And if you do that, then whatever charge you put there will experience zero force because Q times 0 is 0. And if you wanted to find the magnitude, by the way, go back, you want to find the magnitude of the electric field, you take this squared plus this squared and take the square root. Okay, and you want to find the angle, you take the inverse tangent of the y component over the x component. And you can tell that this vector is directed in the fourth quadrant. You will get the same angle or the same direction for the electric field as we did for the force problem. When you multiply by Q, if Q is positive, the direction of the vector will not change. If Q is negative, the vector will flip by 180 degrees. All right, thank you.